a power function is one of the form f of x is equal to x to the power r. So this is a power function, and the most important thing to understand about power functions is that the base is the variable and the exponent is fixed. So this is a power function with constant exponent r. Constant exponent r. So the base is the variable here. So, unsurprisingly, because the only freedom we have in choosing a power function is the exponent, that's going to dictate the properties. So the key fact the properties of f depend on the value of r, unsurprisingly. Now, we've already seen some power functions, namely, what's going on? Namely, the polynomials. So polynomials basically are sums of power functions pretty much, at least multiplied through by constants as the coefficients. And a power function would of course be a polynomial if r was a non-negative whole number. But r can be anything in theory here. And we've got to be careful because we're going to see for different r's we're going to have quite different behavior. So I think the first thing we should do is just go through some simple examples before trying to kind of capture all potential properties. So let's do some examples. Okay, so let's do 6 examples. So let me just take this and duplicate it a few times because we're going to need a few of them. Okay, let's do one super simple one we're all very familiar with, x squared. So y is equal to x squared. Seen this many times. This is a parabola of the following form. Of course, it's an even function, so it's the same on both sides. Or it's a reflection in the y-axis. Okay. Another simple example, x to the power 1. Well, that's just y is equal to x. That's this straight line. Y-intercept 0, slope 1. Other example, well, x to the power half. So that, of course, is the square root in radical notation. Square root in radical notation, what does that look like? Well, that looks like essentially the reflection of this in this line, as we've talked about before with inverses. So it looks kind of like this. Dot, dot, dot. And the domain, notice, is all non-negative numbers, 0 inclusive, because you can't take the square root of a negative, not in the world of real numbers. If I take the cube root, though, so y to the power, or x is equal to y to the power third. So written in radical notation, it would be this. So I just want to give some examples that show you all the different things that can happen, really. Or quite a few of the different things that can happen. So this one's interesting because it would be, so this is the reflection. So this is the inverse function to x cubed. So it's the reflection of x cubed in this line. And it looks like the following. It looks kind of similar to the square root, but it's got a negative piece because you can take square roots of negative numbers. So it's similar, but it's got this kind of thing going on at the back as well. Really interesting example. What about if we had y is equal to x? Okay, we'll do 2 over 3. So this one, I suppose, if we're going to use radical notation, well, we could write it like this. The cube root of x all squared. That's kind of how we defined this exponent function, this exponent term. So what does this look like? Well, this actually looks, again, quite similar to the square root and the cube, at least if we're going in the positive direction, this kind of business. But then the square here is really interesting. Because there's a square, that actually makes this an even function. So what happens is this is an even function, so it has to have this kind of nasty corner at the bottom. So it's a reflection, basically. Can I draw this a bit better? Looks like this. So interesting. Bit more difficult. So that 2 at the top really changes things quite a lot. Finally, we could have something like y is equal to x to minus 1, which is 1 over x. We've seen this one before. This is the reciprocal function, it's often called, and it looks like this. So it's a rational function. I suppose it's got an infinite discontinuity at 0, if we've done the rational function section. So let's just kind of take a step back from all of these. Look at the difference between them. Some of them are very similar, obviously, but there's also kind of pretty big differences between them. So what I want to do is essentially to try to completely describe to you all possible cases so that we have a one-stop shop for all power functions if you want to know their basic properties. So these are good examples to have in your mind. Let's do the general properties. So general properties of f of x. Okay, what we're going to do is the following. We're going to do x to the power a fraction a over b. I'm not going to do powers that aren't fractions because things become quite a lot more complicated. Let me settle on some decisions about this fraction. So the way I'm writing this fraction, remember fractions aren't unique. 2 divided by 4 is equal to 1 divided by 2. But what I can do is like cancel off common factors. So I can always do that. I can also always make the bottom positive. So let's assume a over b is a fraction. So a and b are whole numbers. And b is greater than 0. What am I doing? b is greater than 0. A fraction. So a ratio of whole numbers. No common factors. So if it was a half, it would be 1 over 2. Okay, it wouldn't be 2 over 4. So just as an example, a bit more complicated, I wouldn't write 8 divided by 6. I would write what? I would write 4 divided by 3 instead, cancelling off the 2. So this would be your A, and this would be your B. And if it was negative, you would make the A negative, and you'd keep the B as positive. Okay. So I want to take us through all the possibilities of what can happen here. All the possibilities of what can happen here. So first of all, let's think about a ridiculously simple case where A over B is positive, of 0, sorry. So let's start off with that special case. Okay, so if A over B is equal to 0, if A over B is equal to 0, so this is just x to the power 0. Now, this one's a little bit interesting because if it's x to the power 0, of course, any non-zero number to the power 0 is equal to 1, so this should just be 1. We run into a bit of problems at 0 because 0 to the 0 is often undefined, But when we're talking about the power function, we usually just define 0 to the 0 as 1. Otherwise, the power function would be very strange. So I'm just going to draw the graph just to make sure we understand. So it's just the flat line. So this is y is equal to x to the 0, which is just going to be equal to 1. And at 0, let's just say it's equal to 1. Let's not say it's undefined. That's a bit messy. That's an extremely uninteresting function. It's just a constant function equal to 1. I'm not really going to dwell on it. So instead, let's think about what happens when I'm positive or negative. So this is going to break up into kind of two cases. Okay, so we're going to have, we'll do A over B is greater than 0, so that would mean that A is positive according to my conventions because B is always positive. And this one we'll do A over B, we'll do it as less than 0. Now, as you've seen up here, if we look at these exponents, I think we're going to have to break things into cases depending on whether or not, for example, the denominator B is even or odd, and also whether or not the numerator is even or odd, because we can see differences, right? Here, the denominator is even, and that kind of was kind of a square root type situation. We're not getting any negatives in the domain. Whereas here, it's cubic, so it's an odd number, so we can take cube roots, for example, of negative. So we've got differences there. But then again, we've got differences between this and this. And that feels like it's because of a difference between the numerators. In one case, it's 1, in the other case, it's 2, so odd and even. So we're going to have to break it up into cases. So this is going to be pretty confusing, but I think we have to do it to be comprehensive here. So, first of all, I'm going to break it into, well, if B is even. So if B is even. So just as quick examples, so e.g. we could have a half, or we could have 3 over 2 or minus 3 over 2. No, we couldn't have minus because we're positive, aren't we? We're assuming I'm positive here. Something like this. So let me show you what the graph has to look like in this case. So if you're down this situation, the graph, so I'm going to have to keep these pretty small. Maybe a little bit larger than this. So give me one moment while I just work out how much space I need. I'm going to need 6 cases, you're going to see. It's going to be very confusing first off. I'm going to take us through this very slowly. Okay, so here's what the graphs are going to look like. So we'll start off with this guy, B even, A over B positive. Well then, the domains are going to be positive numbers, so you're not going to have anything on the negative side because you can't do things like take square roots of negatives. And how it curves is going to depend on the size of A over B. So, for example, if A over B is greater than 1, then you kind of curve up like that, kind of like a quadratic. Okay, so this would correspond to A over B bigger than 1. But if A over B is strictly less than 1, then you curve like this. Dot, dot, dot. So this corresponds to A over B. Well, remember A over B is positive. strictly less than 1. Okay. And a over b couldn't be equal to 1 technically here because of the fact if it was equal to 1, we would need to have a positives or a even as well. And we can't have a even because a and b are meant to be, they don't have any factors in common. And if they're both even, I could take a factor of 2 out. So just quickly, some important points. They're exactly the same at 1 and they take the value 1 here. So that's the basic shape there. Next possibility. So now we could think about b being odd. And if b is odd, it again breaks into 2 parts. Depending on if a is even or a is odd. So I told you this would be pretty confusing. But I think it's really good at one point in your life to go through this really carefully. So a is even or a is odd. So the even case is maybe the more interesting. So if b is odd, that means the denominator is odd. It's like taking a cube root of something. And I can take a cube root of anything. So in this case, the domain is going to be the whole thing. But now the a is even. So that basically raises everything to an even power, which makes everything positive. So it's kind of like this example. That's going to be the basic shape. So what you'll end up getting is the following. You end up with the following. It's very, very similar to what we have on the other side. In fact, I'm going to use the same color scheme. So you have, it looks kind of like this. Where am I? So if you're strictly bigger than 1, it kind of looks like this. Exactly the same thing. And it's even. And if you are strictly less than 1, then it kind of looks like this. It's kind of crazy. Okay, with exactly the same kind of key points. You've got 1 there, you'd have -1 there, you'd have 1 there. Okay. Let's move this over ever so slightly. So that's in this case here. All right, so what about if you're odd? Well, if you're odd, then basically it's the same thing, but this now is going to happen in the 3rd quadrant. So it's extremely similar, but you become an odd function. So what you would have is same thing here, essentially the same basic shape. And on the other side, it would be flipped like this. Kind of beautiful, really. So maybe I should just do some examples. So here, e.g., I mean, what could we have? We could have a 2 over 3. Let me move this down a bit. It's a little bit too close in. Okay, let me move them all down. So e.g., or 4 over 3 or something here. In this case, could have, well, that's a pretty good example because you could have 1, right? You could have b is 1 and a is 1. So this would correspond to 1 here. So that's one I kind of left out. You could have that straight line like this. This is where this one turns up. And then the other side. Right? So e.g. 1 divided by 1, or I don't know, a third, we've just seen that one. Or 5 over 3. All totally reasonable. And again, the same kind of core points. 1 here, 1 here, -1 here, and a -1 here. It's pretty elaborate looking, I think we can agree. Now what about if I'm negative? Well, this actually is really different. What I'm saying is really comprehensive though. So I know this is kind of, it can be a little bit overwhelming, but it's complete. I'm really giving you everything you need to know. There's no kind of holes in the theory in the way I'm drawing it. So if B is negative, then we essentially get the same kind of breakdowns as before with different behavior. So if A over B is negative, then A is going to be negative because we're always assuming that B is positive. So then what are we going to get? Well, we're going to break it into the B is even case, first of all, just as before. And then we'll break it into the B is odd cases. And we've got the same story as before. Let's break it into the A is even and the A is odd. And let's shorten this a little bit. So let's go through each of them in turn. So example, e.g. So it's a negative and the base is even. The top can't be even, so you could have -1/2 here. Totally reasonable. -3/4. We couldn't have even over even, remember, because we're assuming A and B don't have any common factors. So in this case, basically the shape is always the same. I could make a small distinction between if it's between 0 and -1 or -1 onwards, but I think for the sake of simplicity, it kind of has such a similar shape, we might as well leave it. So in this case, shall I do it with a different color? Let's do them all in purple. It looks like this. And that kind of moves around a little bit. But it's always this, and it has to be this because it's even on the bottom. It's like taking a square root. And again, it always contains the point kind of here, 1, 1. It's always in there. Next one, if A is even and B is odd, well, it's the same thing, but now the A even makes it an even function. But just before I do that, here are some examples. You could have -2/3. You could have, what is -2/1? That's perfectly reasonable. So it would be x to the -2, so 1/x squared. So that may be one you've seen before. So this guy, again, it looks incredibly similar. On the positive side, and it's reflected. It's an even function, actually, as we'll discuss in a second. Okay, and again, you've got your kind of key points here and here. Got 1, -1, and a 1 here. And lastly, odd, odd, and negative. This looks like, well, this, for example, let's just do it. This could be A is -1, B is -1, or B is 1. So that would correspond to x to the power -1. So e.g. you could have -1, or you could have -1/3, something like that. So this looks like the kind of the reciprocal function I've just described. It's essentially that pattern. Okay, neat. So again, finally, you always have these kind of core points here. So we've got a 1 here, -1, -1, 1. Right. So that's all the possibilities, honestly, right? That's every single possibility. Those are all the graph shapes. You don't really need to sit and memorize all of those, but it's good to, at least at one point in your life, be aware of all the possibilities. So what I want to do now is just go through all of my core potential properties, things like domain, range, increasing, decreasing, and all of these are going to follow from the graphs, essentially. So the graphs are going to tell us all this information.